Welcome, everybody. Aloha. Thanks for being here for our April Slice of PI-CASC monthly seminar hosted by the Pacific Islands Climate Adaptation Science Center, or PI-CASC. I'm Brad Romine. I'm the University Consortium Deputy Director of PI-CASC. Before we get started, I want to thank everyone, those of you that attended the Hawaii Climate Week last week, either in person or online, including our PI-CASC Graduate Scholars Symposium, which was held on Thursday last week and helped us to make that event a great success. Recordings of that event and the rest of Climate Week conference will be linked to PI-CASC's event page real soon. This Slice of PI-CASC seminar series provides a platform for sharing state-of-the-art climate adaptation research and science to management applications in Hawaii, the U.S. affiliated Pacific Islands, and beyond. For those of us joining us in person, in keeping with our theme, Slice of PI-CASC, please help yourself to some pizza pies arriving right now. Great timing. We also have a dessert pie provided by Rachel, for those of you here in the end. Again, thank you. Again, keeping with our Slice of PI-CASC theme. This presentation, you probably got to notice, is being recorded. It will be available online on PI-CASC website under news and events in a day or a week or so. Sorry, a few days to a week or so. And for those of you joining us online, please keep your microphones on mute during the presentation. We will have time for questions following the presentation, so please feel free to leave those questions in the chat online as we go through, or feel free to raise your hand or chime in after the talk. So with that, it's my honor and pleasure to introduce Dr. Dean Gesh, who will be presenting on characterizing inundation risks and enhancing stakeholder capacity for coastal inundation assessment in the Marshall Islands. Dr. Gesh is a research physical scientist with the U.S. Geological Survey, conducting topographic science research at the Earth Resources Observation and Science Center, EROS, in Sioux Falls, South Dakota, where he is the principal investigator leading the terrain monitoring and modeling focus area in the Integrated Science and Applications branch. Dean's research topics include sea level rise vulnerability assessment, topographic change analysis and monitoring, hurricane storm surge mapping, elevation data accuracy assessment, and topographic data development and application. Dean's education background includes a PhD in geospatial science and engineering from South Dakota State University. As you've gathered, Dean does not live on an island or a coastline. In fact, he lives about as far away from an ocean as you can get in the U.S., but he did grow up on a coastline, a Great Lake coastline, in Lake Michigan in Milwaukee, Wisconsin. So that must have had some effect on Dean's study area and his later professional work. So aloha, Dean. Thank you very much for being with us here today and sharing your work with us. I'll pass it over to you. We'll give you a moment to go ahead and get your screen share going then again.
Okay, thank you, Brad. Yeah, we'll get the presentation up here. Okay, looks good on my end. I trust that the slides are displaying properly there.
Yes.
Looks good, Dean. Thanks.
Okay, good. Okay, thank you everybody for joining, and thank you, Brad, for that that introduction. Yes, I'm in South Dakota, so as Brad said, about as far away from an ocean as you can get, but glad to be with you today and presenting. Geography first. I'm a geographer by training, so we'll set the stage here. For this group, probably not unknown where we're talking about in the Marshall Islands, but I'd like to start out with maps, definitely. So the Marshall Islands, Republic of the Marshall Islands, right there in the west central Pacific, right in the middle of that map. And then as we zoom in, a couple of places that we're going to concentrate on today, focus on today, are some of the outer atolls and one atoll or one coral platform island, Mejit, and then a couple of the atolls we'll zoom in just a second, you can see. And then we're also going to talk about Madro a little bit, the capital, and you'll see why. So these are the areas we're going to focus on today after we get through some background material. But Or Atoll, Ebon Atoll, Likiep Atoll, and then Mejit Island. And pardon me if my pronunciation of these isn't just exactly right. And then a couple of smaller areas within each, the inhabited islands, inhabited and built up islands in each of those atolls. And we'll focus on those as we move on. Also with the geography, talking about, since we're talking about coastal hazard assessment, set the stage here. Again, a lot of this is probably known, but it's good to review the conditions in this area, sea level rise, global sea level rise. It's an area that's particularly at risk of that. And just some graphics from some of the IPCC reports that show that. So I don't know if you're seeing my mouse pointer come through here, but in the Central Pacific, it's an area where the rates of sea level rise are higher than the average, the global average sea level rise. That's what's shown here. Some more recent graphics from the most recent IPCC report, AR6, kind of show the same thing. If you look, no matter what scenario we're looking at in the Central Pacific, it's an area where the sea level rise is definitely a factor and greater than in other areas. As we look at the instrument record, just another graphic. I really like this one. This one shows the recent sea level rise in what we call the instrument era since the early 1990s. In this case, goes to 2014, so about 10 years ago. And again, RMI, Republic of the Marshall Islands, right in the middle there. And as you can see, greater change, the high end of the range of change in that area in the Central Pacific. And then in the last 10 years, again, this shows information from the instrument record satellite radar altimeters, and then also the dots are long-term tide gauges, which show the same thing here in the same general area where RMI is located in the West Central Pacific. And it's not just the global mean sea level rise, but the events that come. So all the scenarios show how sea level rise is increasing in that area, but this is a schematic, kind of an idealized diagram which shows individual events. So short-term events or episodic events, high tide flooding, storm surges, that sort of thing, and those occur in addition to the global sea level rise, so add to the risk of inundation in these areas. So some background and context for this project that we're talking about, from the Marshall Islands National Strategic Plan, last couple versions of that. And this is, again, well known and well stated, but inundation mapping and coastal flooding, coastal inundation are certainly significant risk factors in the Marshall Islands, and that's recognized in these documents. And then also the other part of the project is the capacity building and stakeholder engagement for doing this kind of mapping and this kind of analysis is important. The other part is this ridge to reef, some context of where this project comes from. Ridge to Reef project that was sponsored, funded by the Global Environmental Facility. It's the Ryman process, doing community-driven resource management. So it's an implementation of that to operationalize that, as the second point there says, through integrated management of terrestrial and coastal resources. So that's a good context. And the major partner in this is the Marshall Islands Conservation Society, or mix. And this is a good diagram of that Remluck process and where this project fits in the context of that. This comes right from the mix website. So collecting baseline scientific information, and in this case, terrestrial surveys and island height and flood risk assessment. So bring some context to where this activity falls. So this is what resulted in the project that we're talking about today, enhancing stakeholder capacity and the for coastal inundation assessment. That's the project sponsored by PI-CASC. So as we talk about coastal inundation exposure, I think it's good to remind ourselves of how exposure is defined. This comes right from IPCC. So it's the presence of people and environmental resources, that sort of thing, in places that could be adversely affected. And obviously that includes coastal locations subject to coastal inundation. So good definition of exposure there. And then as we talk about coastal hazard assessment, one of the big things is quality geospatial data are needed for these coastal hazard exposure assessments. There's been some existing assessments and they really lack the spatial detail that's needed for adaptation planning. That's the real goal, is for adaptation planning. And part of that is due to the coarse nature of the topographic information that's used. So high resolution, higher accuracy elevation data, remote sensing derived facilitate a much better quantitative exposure assessment. And one of the things we do is account for the uncertainty of the data. That makes these assessments more useful. So as we talk about uncertainty in sea level rise assessments, that uncertainty comes from several places, several factors or components. The climate change scenarios themselves, certainly the contribution of ice melt in the polar ice regions, and then also in how we define the water level when we're measuring water levels. Obviously, it's in reference to a datum, so there's some uncertainty there. But the big one that we're talking about is uncertainty in the input elevation data and accounting for that. So I'm going to dive into the technical a little bit here, just as a necessary background, because that sets the stage for the elevation data that we're using in these assessments. So these coastal inundation assessments that use a digital elevation model, there's uncertainty associated with that, and that affects how these assessments are done, specifically selection of the assessment parameters, and then how that's mapped onto the land surface. So the big one is the increment of the water level increase that can be modeled effectively, and we'll see how that is controlled by the elevation data and how to do that properly. So just a couple of quick things here. When we talk about uncertainty with elevation data, we have to talk about error, elevation accuracy, and how we measure that with error metrics. A root mean square error is a common way to do that. That talks about the quality of the elevation data. And then there's ways to translate that to other metrics here. So back to some elementary statistics about error distribution, and you'll see how this factors in. So this leads to a concept that we call the minimum sea level rise increment, or the minimum increment of inundation that can be effectively modeled by use of elevation data. So that's the smallest increment that's supported by the vertical accuracy elevation data. So it's based on a concept of contour line accuracy, and there's some standards that help us define that. So we can talk about the accuracy of the elevation data in terms of contour lines, because raising the water on a DEM to do modeling of coastal inundation is inherently a contouring operation. So we can use this measure of contour line accuracy to talk about to use the what we know about the accuracy of the elevation data to lead to a better mapping of the impacts from water level increase. So the bottom line is the water level increase that you're modeling should not be so small that it's the noise of the elevation data or in the error of the elevation data. And that's the way we do that. So again, some simple statistics, simple formulas that equate the accuracy, the error of the elevation data to this amount that we can model. And there's simple ways to do that and put a confidence level in on how well we can do this mapping. So here's an example of 1 foot of sea level rise. And this tells us how accurate the elevation data has to be to map with a certain level of confidence. So plugging those all that information in, you see you need about an 8 centimeter vertical accuracy to map a 1 foot of sea level rise at a very high level of confidence, 95% confidence. Be a little bit less at a lower level there, but use that example because that's commonly done. A lot of this is the background for this is documented in a series of papers and studies where this has been done and applied, and we'll show how that's done for the work that's being done in the Marshall Islands. So I'm going to switch over to Majuro. Not one of our study areas for this, but previous work, because this shows the methodology and the important considerations that were done for the current work. So it's a good illustration of that. Now it's just some examples. Again, Majuro is low relief setting, just like these other ones, more urbanized, so dense urban population, but you can see from the photos here there, and it's a good representation of the other areas. Again, very low relief atoll environments. So the survey that was done here was with drone photography, collected very high resolution photography, and then also control points, GPS control points, and ground survey control that are very important. That's all put together. There's just some diagrams of those different things that were collected in the surveys, the photos and the control points, and that's used to make elevation models. So the way we do that is with structure, what's called structure from motion. It's a photogrammetric way, stereo photogrammetry, but in addition to just using 2 photographs, uses many photographs to construct the topography, and we can produce very accurate photography or accurate elevation measurements from that. And it's done with a process here that shows a bunch of different steps that incorporates this all. In the end, it makes what's called a point cloud, which is like LiDAR data like, and then that's produces an elevation model. There's an example here of the portion of the Majuro Atoll where you can see the imagery that was collected by the drones, processed through to the structure for motion process to make the digital elevation model. But when we talk about, so the accuracy again of the elevation is very important. And that's what's been done here. So the Majuro DEM has an elevation accuracy of about 7.5 inches, about 19 centimeters. And that's important for when we do this modeling, because you can see in the very low relief environment there. There are other global elevation models that are much coarser. They have been used for this type of analysis, but really aren't appropriate for that because they have a much larger error associated with them. So schematic of the error bars. Again, it's not to scale, but it does show how they're not really appropriate for high accuracy, high resolution modeling of the inundation. So the way we do this is to incorporate what we know about the error, and with confidence, then we can map these small increments of elevation of water level increase. In this case, just a little over 1 foot above the high tide line. And that's what was done for the Majuro study there. Again, just a diagram that shows how we can associate a specific confidence level with that. That's very important to do. Once that's done, then the next stage is the spatially explicit inundation mapping, or constructing the coastal inundation assessments. That can be done in a number of ways. I'm not going to go into a lot of detail here, but deterministic is a simple way that's been done, where it doesn't incorporate the information accuracy, the elevation data. So it's really not the best way to do it. There's another way, modified deterministic, where you can use some information about at least the range of vertical error. The best way to do it, and the way that's been done for this study, is probabilistic, and that's where we model the error, the error information, and then apply that in what's called Monte Carlo simulation to come up with results that are probabilistic, and that incorporates a lot of information from the elevation data. So just a quick diagram about how that's done. And again, this is all good background, because this is what was done with the current study on the other locations that we'll talk about in just a little bit. Is the elevation data itself. There's the accuracy is done by comparing against VP's validation points. So we get an accuracy assessment there. There's error statistics, and then those error statistics are used for a random selection, what's called random fields. Basically model that error and then associate that with the elevation, and then do what's called a realization, and then input that into the inundation mapping, water level, and then we get our inundation map, or inundation grid. So that's done many, many times. That's done once, twice, 3 times. In this case, it was done 1,000 times, and then that gets gives you a series of maps that then characterizes spatially where that error falls on the land surface, what we know about the DEM, and that can give us much better information about the projected flooding risk, coastal inundation risk. Got some examples coming up, which I think will help show how that works. So here's the inundation probability for 2 areas we've zoomed into on Majuro Atoll. And as you can see, it's a continuous variable there. So probability from 0 to 1, or 0 to 100%. In this case, it was done for a specific level of 3.75 feet of increased water level. And then that can be thresholded or segmented to a specific probability. So in this case, it was 68%. So likely, so these are the areas that are likely to flood or be inundated at this water level, 3.75 feet. And so there's a known probability associated with that. So this incorporates the error of the elevation data and gives us a lot better map of where potential flooding could happen at a given water level. One thing to note, and again, I remark on this because it was done with the previous, or it's being done with the current study as well, is the type of inundation. So there's a distinction between marine inundation, that's what's shown in the dark blue, and then what I've called low-lying areas, or light blue. On the little diagram that popped up there, it's called groundwater inundation. So these are areas that are below that elevation of 3.75 feet, but they're not connected with a surface hydrologic connection to the ocean. But they are important because as groundwater rises from sea level rise, they can also become inundated. It can also fill from, they're the lowest areas that are going to fill with precipitation. So this is how these inundation maps are made with this probabilistic approach. If you compare kind of the bottom half of the graphic to the top half, you can see the high probability areas, those that are in red, from yellow to orange to red, those are the areas that, again, are above 68% chance of flooding. And again, this can be done at any probability. And you'll see some graphics later that show a 95% probability. So the areas where that are labeled as extremely likely, or we're really sure are going to flood at a given water level, given what we know about the accuracy of the elevation data. Okay, so a lot of background information there, but now we're going to apply it to the current study. So this is really the main three parts of the project, of the current project, and they break down kind of nicely here. So the survey and data collection. So this is the on-site data collection. This is the ground control points that I mentioned, and then the drone imagery. So it's a ground survey and it's an aerial survey. And then that's the data that feeds into the DEM production and what's called the ortho image mosaic, or the rectified image that comes from the drone. That's comes from the structure from motion process. And then those DEMs, or the elevation data, then feed into the inundation processing. And that's where we assess the accuracy of the DEM. And then we do this Monte Carlo simulation to produce the inundation exposure grids, and then characterize that all with the statistics and present it as statistics and maps. So as far as this project, it breaks down nicely into these three parts here. So the survey data collection, that's really headed up by the Marshall Islands Conservation Society mix. And so Judson Nelson was the lead of the team that did that. Got a bunch of details about that in just a minute. And then the other big partner on the project is University of Hawaii at Hilo. That's Ryan Peroy's group, and we're responsible for producing the DEMs and the imagery that came from the survey. And then the USGS part is the inundation processing part, and that was myself and a number of us from USGS. So you'll see how these three pieces fit together. So a lot of collaboration and good cross work among those three groups there. So again, back to our specific study areas and the islands within those atolls. These are the survey dates. So Judson and his team spent an extensive amount of time on each of these sites, conducting these surveys at the timeframes that you see there. So collecting the drone imagery and the ground survey points that are both necessary components and very important. So a lot of good work by that team to do that. Very important and necessary. Couldn't do the mapping without it. Here's an example of one of the planning maps for the ground, for the survey planning maps. This is Likiep Island and Likiep Atoll. And so a couple things I want to point out here. You see a bunch of dots with labels. So those are this was the plan to collect the ground control for the ground survey. And then also the polygons that you see in different colors are the flight plan. So 3 different days of flights there. And it's real important to do this planning properly. You can see there's overlaps among the flight days, and there's control points in the overlap. So the mixed team did a great job planning this. There's a distribution of 2 different types of control points. So the GCPs, or ground control points, those are the ones that are used to rectify the imagery and georeference the imagery, obviously place it in a very proper place. So each of those points are surveyed very precisely on the ground. And then the other points, the validation points, are not used in the production of the imagery and the DEM, but they're independent validation points that are necessary for the crucial accuracy assessment, so we know how accurate the elevation model is. But these are all very precisely surveyed ground points and are very important to the process. So a lot of work collecting this in these environments. Here's some pictures from Judson and his team that show this work being done. So the drone down in the lower left, you see one of the control points. That's an aerial target, that black and white target. So that can be seen from the imagery very precisely, very easily, very clearly, and then that's surveyed. So we have a very precise latitude, longitude, and elevation associated with that. And then likewise for the some of the validation points that you see in some of the other imagery there. I like the picture in the middle. Obviously long work days there. You can see they're finishing up their survey by the headlights of the truck in the dark there. So a lot of intense field work. And then the picture at the bottom, one of the oblique photos from the drone itself just shows the environment that the work was done in. So heavily vegetated. So that's where the planning is important to be able to control, select control point sites where the canopy is open enough to be able to get a good GPS reception. So a lot of work goes into that. Okay, and then to the next step, these are the DEMs. So these for two of the places, just displayed as grayscale images. So the lowest elevations in each case are the darker tones, and then the lighter elevations toward the whites are the highest elevations on these islands. So this is where the control points were used, the validation points, I should say, and those are the yellow dots that you see on each of the maps there for those two islands. That's where we calculate this elevation error, as I talked about before. So you see this root mean square error, the common elevation metric, and then that's translated into this sea level rise, the minimum sea level rise increment there at 68% confidence, and that's in this case expressed in feet. So we can see very accurate elevation data. Really what you want to see is you want to see a mean elevation error, the one column there, very close to zero, which we are in most cases. And so we're looking at elevation data that's accurate to within, basically 6 to 12 inches of elevation accuracy, which is very good from these drone collections. Drone imagery collections and then the DMs that were made from that. And then that's translated into these increments. So the column on the right is the increments that were used for the modeling, rounded to the nearest quarter foot there. So you can see very fine amounts of modeling for increased water level, which is what these high accuracy elevation models allow us to do, and are quite necessary in these low relief environments. So the inundation modeling parameters that come out of that, this is one thing I wanted to mention. Again, on the lower right are the increments that were used for each of the 5 islands to model the inundation, so 3 different levels. But then also where that inundation starts from. So hopefully you can see it on the slides coming through, but in each of those, it's a picture from the drone, the aerial image from the drone, right near the shoreline, includes the shoreline. There's a blue line, a dark blue line that is actually a contour line from the elevation model. And that's where above that elevation is where the inundation was started from. Now, generally, when we do this, what we did in Modro, we have quantitative tide information, tide gauge information, long-term tide gauge. We start at what's the high tide line, or the average high tide line, or what's known as the mean high water elevation. Now, on these outer islands, we don't have tide gauges, so we don't have a quantitative measure of the tide record there. So these lines, these blue lines where the inundation modeling starts from and is modeled above, are interpreted from the imagery, and that's to be the top of the beach and the coastal vegetation line there. So you can see how that was done. Now onto some of the actual products for some of these islands. So this is the inundation products. So the orthomosaic there you see at the top, so that's all the imagery stitched together. You can see where the airport runway is, and then the development, most of the development on the upper right, building sites. AOI is area of interest. In this case, it was the entire island. On some of the islands, that was limited to just the built-up areas. And then the DEM displayed as shaded relief. So you can see, again, very flat area, but you do see some change in the topography, again, from this very accurate elevation model. Now onto the actual inundation products. So these are the same as what was done for Madro there. You can see this probability of inundation at the top. And again, this was one of the, I think the middle scenario that was done for this island, Likiep Island. So 2 feet. And then again, that's scaled or thresholded, I should say, into the 2 maps in the middle and the bottom. So 2 feet at 66% probability, and then 3 feet. So higher, the higher, the highest of the 3 inundation levels that are modeled again through this Monte Carlo simulation. So we have this probability. So we run this 1,000 times. Basically, we're saying these locations that are showing in dark blue, 66% of the time they were indicated as being flooded. So that's where the 66% probability comes from. Again, incorporating what we know about the accuracy of the elevation data. So even though these are very highly accurate elevation models, they still have error associated with them. And then we can model that to make these really precise inundation maps. And then of course, statistics associated with that. So just the, excuse me, the area expressed in a couple different units for the different inundation scenarios. So I'll kind of highlight these places on the right. You can see at 1 foot, actually very small percent of the island is affected, more at 2 feet, and then a fairly significant amount as we move to 3 feet of inundation. So this mapping approach gives us statistics, but then the maps that you saw give us the spatial representation of where that comes from. So that's what's obviously really needed for adaptation planning and risk assessment. Okay, one of the other locations, nice series that fits on there. Excuse me, series of images there. So again, our orthomosaic, our area of interest, and then step through from the middle to the right, the 3 different levels, again, at the 66% probability of inundation, again, showing both the marine inundation as dark blue, and then this low-lying areas or groundwater inundation as light blue. So at the lowest level, you can see there in the middle, 1.5 feet, you can see there's only a small area along the shore that's affected. There's a low area in the center of the island that would be affected by groundwater. And then as you increase to the right 3 feet, you can see now that area becomes connected. The inundation level is high enough, if you will, to connect that part of the island. And then obviously to the right, even more areas. So this is where modeling the groundwater inundation or these low-lying areas separately from the marine inundation shows how this progresses, you know, how they become merged, if you will, at the higher levels of inundation. You can see in this particular case on Mejit, a lot of the built-up area isn't covered by the inundation, even at the highest levels, but certainly there's a significant impact on the airport runway in the center of the island. And then one more example here, one of the other islands, again, just to show side by side. So there's our probability of inundation at 2.5 feet. This is the middle scenario for Orr Island. And then in the middle is 66% probability. And then at the same level, now we're at 95% probability. You can see the area that actually decreases, again, because if you think about it, it makes sense that these are the areas we're really, really sure this is the most accurate elevation data in this part. So it has to be very accurate to be really sure that it's inundated at that projected level of 2.5 feet. So again, these examples of 66% and 95% are what have been generated, but that could be, you know, for other planning purposes, that could be a different level. It's easy to do to threshold that from that full probability of inundation that you see on the left side there. All these data sets are soon to be available. So there's some 110 geospatial data sets, GIS data sets, all 3 different scenarios, different probabilities, for all these 5 different islands. It adds up to a lot of data, but will be available to characterize the inundation risk and for use in adaptation planning on these locations. That's will be released through the USGS, what's known as the science-based data release, but also obviously delivered and available to the users in the Marshall Islands there. So again, what's the need for this? Adaptation is the goal for all of this, and adaptation planning. So the full-blown adaptation plan from the Marshall Islands that came out last October, I believe is when it was finalized. There's some direct mentions in here of this need. There's been planning done for some locations, but this lack of accurate data on island topography, on elevations, it's known, and so that continues to be a need. And this work that we're doing addresses that. Again, there's global elevation models, but it's just not accurate enough, and it really leads to a lot of kind of uncertainty or rough estimations of that. So, much better data is needed. Here's an example of some of these outer atolls where an assessment's been done of 3 different levels of an initial assessment of 3 different levels of inundation. And it notes right there on the bottom that's highlighted that it has large uncertainty bands because of the coarseness of the elevation data. So here's 3 that, the 3 that we're working on now. So it's a little bit hard to see, but if you can see, there's error bars, thin error bars that are associated with that, and they're huge. For instance, for Mejit Island, it looks like about 5% of the area is affected by some, even at the highest level here of 2 meters, but there's a huge error bar associated with that because of the coarseness of the elevation data that was used. It goes anywhere from, about 5% up to about 50%. So that's really limited for use in that kind of adaptation planning, because it's got such a huge error bar associated with it. So that's the advantage of having this elevation data that's being done here. And then also the national climate assessment, the 5th national climate assessment in this area really echoes this, or says, makes this the same statement that, inundation and, sea level rise and events, high water events will continue to be, a risk and increase in frequency. But the way to model these best is to have this high resolution elevation data. And that's a need for a lot of islands, and that's been demonstrated here. So we're addressing that need, and more needs to be done with that. Yeah, a lot of thanks go to a lot of participants here. I've probably left some off, but a lot of names here that contributed quite a bit to this activity. The training and capacity building is a big part of this, and a lot of that was done by a number of these individuals here. So the survey collection, both the aerial survey and the survey point collection, that was instructed by Ryan Peroy, with teaching about the drone collection, drone imagery collection and processing of that data. So the imagery is useful for producing elevation models. Ed Carlson from NOAA instructed on survey collection and processing, and then all the things that go into that, the field planning, to have these points in the right place and collect the imagery in the right. And then the inundation modeling, the use and interpretation, that's our part that we're instructing on. We will have June on-site training for the users coming up in June, and when we deliver the data, and also instruct on interpretation and use of this inundation modeling results. So that's a big part of this. A great example is the Mix has developed and now uses protocols, drone mapping protocols, very detailed drone mapping protocols, and then terrestrial survey protocols, very detailed directions about how to do this the proper way. And then so that'll be applicable for future work. So really glad that's a good part of it. So I'll end there with thanks to all these individuals, and appreciate your attention, and happy to address any questions or comments. Thank you.
Great, thank you, Dean. We have some time for questions. I see one in the room from Hal, first hand up.
I got actually two questions, and they may be related. First, I want to understand when you're talking about like 2.5 feet at 66%, you're talking about 2.5 feet of sea level rise over the mean low tide, mean tide?
That would be over the mean high tide.
Over the mean high tide. Okay. So
Yes.
when you do the Monte Carlo studies, I'm not quite sure what variable is being randomized in there. I'm not sure what that's doing.
Right. Okay. Yeah, the variable that's being randomized is the elevation error. So by doing the accuracy assessment of the elevation data with the high accuracy reference information, we get precise information about the accuracy of the elevation data, what that error distribution is, basically the mean and standard deviation, if you will, of the error distribution. So that allows us to characterize that error. So in each of these realizations, each one of the Monte Carlo runs, then that error is added to the DEM and makes a fully plausible, what's called realization of the elevation model with the error associated with it. Then the inundation mapping is done on that, and that's stored, if you will, and then it's done again, and then that's how we get a full representation of the error distribution, how that's reflected into the spatial mapping of that particular water level.
Thank you. It was a very good and interesting talk. Thank you very much.
Another question in the room from Chip Fletcher.
Hey, Dean, this is Chip. Nice to see you again. It's been a while.
Yes, Chip, thank you.
Great talk. Where are you guys going to be moving to next? When's your next mapping target?
Good question. I know there's other areas, there's other atoll locations that are in need of this information. I don't know the exact one, so I can't answer that exactly, but there's definitely a need for this type of mapping in other locations in the Marshall Islands.
Thanks. We'll come back to the room, but I want to see if there's any questions online before we come back to the room. Feel free to just chime in or raise your virtual hand or type them in the chat. Anybody online with a question? Heather, go ahead.
Sorry, I was on mute.
There you go.
Thanks so much, Dean. It's great to see you.
Yes, thank you.
Yeah, I did and hear everything. I think it would be great to hear a bit about how the work is being received and where it could be useful for the folks in RMI. And I know we have some of the mixed folks on the call too, but yeah, if you had any thoughts toward that.
Yeah, again, a good question. I know that the results are to be used in in the adaptation planning for these areas, the overall ridge to reef project specified these 4 locations and one additional atoll. I think it was Wotho Atoll, but we didn't have the same data collection that was done there. So yeah, a good comment, good question about how they're actually being used, but it is for the adaptation planning for these outer island or outer atoll locations. The Madro example, I mean, that's certainly an area where this information was needed as well. There has been more data collection done there, but the logistics of collecting this type of information are challenging. So that's why important to be able to do on these other locations as well.
Yeah, thanks. And I missed it if you said it, but this was definitely a project that went on through COVID. So
Yeah.
to talk about challenges, that was a real thing, and trying to get the data collected. So thanks to everyone that was part of this project.
Yeah, really, yeah, it was challenging, but yeah.
Hello, everyone. Dean, Heather, hi, everyone. This is Dolores. I'm sorry if it's Judson's name, but both me and him are here. I also wanted to add and let everyone know that not just for the adaptation management of these areas, but also for our contribution as far as terrestrial areas protected to the Micronesian Challenge. So yes, this also is another activity that adds to our list of protected terrestrial areas towards the Micronesia Challenge.
Great, thank you, Dolores. Yes, that's yeah. There was a lot of background in the information of our proposal, and I just touched upon it with the ridge to reef process and all that. But so thank you, that's helpful.
Thanks, Dolores, and the Mix team for being with us today. Also, I see another question in the chat. I'll go ahead and read it. It's from Kelly Anderson Tagarino. Dean, how do your results compare to the USGS HERA tool on inundation results, or does that not directly compare? And I'll add to that a little bit. I was curious also if there is plans to make this data available to one of the USGS sea level rise tools like HERA, or perhaps the NOAA sea level rise tool. I was glad to see that USGS NOAA cooperation in this effort, but yeah, go ahead. Thank you.
Right. No, that's good. Thanks. Yeah, thanks for the question. Yeah, the HERA, I'm going to draw a blank on the while that's spelled out. Hazard. Yeah, I shouldn't even have tried. Right. The A, I'm sure is assessment, but it's similar to that. The information that goes into HERA for modeling, storm impacts or sea level rise impacts, it's the same type of approach. It uses that elevation information. The modeling, I think, that goes into what you see in HERA is a bit more sophisticated because it uses numerical models for storm surge propagation and wind and wave propagation. Those models are data intense. But they use the same approach of accurate elevation data, also use nearshore bathymetry data. So what we've done in these areas is similar, but it's not quite as sophisticated because it doesn't have a lot of the tide information and the more sophisticated model. So it's an initial first cut at inundation processing or inundation assessment. So not sure if that quite answers the question. But to what you said, Brad, about the information about the sea level rise viewer, again, that's the same type of information that goes into it, the quality of the elevation data and understanding the accuracy of it. So it could, if those tools are extended to these areas in the Marshall Islands, right?
Dean, I think I'd seen one more hand in the room. Do you have a question? Yeah, go ahead.
Thank you for the presentation. So you mentioned about the climate adaptation plan. So I'm wondering how your very accurate data apply on such a huge climate adaptation plan.
Yes, good question. I may not be the best one to answer that, but it can be used for. It will be used in various ways, as Dolores said. So, I mean, part of the adaptation plan is just an inventory of what the risk is of inundation at these locations. So that can be incorporated in there. Again, these locations, like the outer atolls and outer islands, are remote from other places where it's been done in the Marshall Islands, particularly Majuro and Kwajalein, Ebon. So that's how it will be used. Maybe a better question for Dolores and the mix team to how that will actually how that's used into in such a big adaptation plan.
Thank you.
Great. We're approaching the hour. We better go ahead and wrap it up. Another round of applause for Dean. Dean?
Thank you.
This concludes our podcast seminar for the month. Please look out for information on the next one, which will be held on Tuesday, May 7th at noon. Our next Slice of PI-CASC seminar will be coming soon. Look out for information on that. If you have an idea for a future seminar, please fill out our survey after you log off with any ideas there. And thank you all, especially Dean, for joining us today for this seminar. Folks, if you haven't had lunch already in the room, please feel free to grab some pizza. There's also a pie that, again, Rachel made for us. So thanks very much. I encourage anybody here on Oahu to join us in person for our future seminars. Thanks again, Dean.
Thank you. Thank you, everybody.